Okay, so today we talk about what might be called abstract vector spaces, not just Rn and Cn, but a general vector space. So what is the definition? So this is really the subject of linear algebra, vector spaces, not the special cases connected with linear equations, but general ones. So a vector space is a set V whose elements are called vectors with two operations. Vector addition and scalar multiplication. And vector addition and scalar multiplication satisfies the following properties. So with two operations that satisfy the following properties. So for vector addition, it's associative. So associativity. This means that for all vectors u, v, w in the vector space, u plus v plus w is the same as u plus v plus w.
Nice man.
Right?
You sound like you're having peace.
Yep. So for all u, v, and w, u plus v plus w is u plus v plus w. There's an existence of an identity, an additive identity. There's some vector we call 0 with the property that 0 plus v and v plus 0 is v for all vectors. We have inverses. For all v, there exists a vector w such that u plus v plus w and w plus v equals 0. And the fourth property is commutativity. For all vectors v and w, v plus w equals w plus v. So vector addition in an abstract vector space, it associates to every pair of vectors u and v a vector u plus v that satisfies these four properties. And we can note certain things. First of all, the 0 vector is unique. If we have two vectors, 0 and 0 called 0 star, satisfy 0 plus v equals v plus 0 equals v for all v, and 0 star plus v equals v plus 0 star for all v equals v. Then if I take 0 plus 0 star, because 0 plus anything is the anything, 0 plus 0 star is 0 star. But because anything plus 0 star is the anything, 0 plus 0 star is 0. So this equation says 0 star equals 0. So that's a proof that the identity, the zero vector, the identity under addition in a vector space is unique. Also, the additive inverse is unique. So if you have a vector v, if v plus w equals 0 and u plus v equals 0, so v is fixed. If you have a vector w such that v plus w is 0 and another vector u such that u plus v is equal to 0, then we can do the following simple piece of arithmetic. So then u, or let's say u is u plus 0, because you can always add 0, but 0 is v plus w, and by associativity this is u plus v plus w, but u plus v is 0, 0 plus w is w, so u equals w. So the additive inverse is unique in any vector space. Okay. And then we have the properties of scalar multiplication. So scalar multiplication assigns to every scalar c and vector v c times the vector. That's scalar multiplication. And scalar multiplication satisfies the following properties. First of all, if you take this number 1, which is a scalar, 1 times the vector v is always equal to v for all v. I mean, this is, you might think it's obvious, but it's not obvious. In fact, it's not necessarily true. But we require that in a vector space that scalar multiplication have this property that multiplying by 1 doesn't change your vector. 2, we have a kind of associativity for all scalars C1 and C2. You can multiply the scalars and then take that scalar and multiply it by the vector. Or you can take the vector, multiply it by C2, and then multiply that vector by C1. And this is always true. And the third is the distributive laws. So if you take C1 plus C2 times any vector, that's C1 times the vector plus C2 times the vector. And if you take C1 times the sum of two vectors, that's C1 times V plus C1 times W. So this is the definition of a vector space. And we've seen examples, Rn, the set of n tuples of real numbers. You can have Cn, n tuples of complex numbers. We have the set of m by n matrices. For a fixed m and n, they form a vector space. But there are other examples. For example, consider the set of all linear polynomials. So that's a polynomial, something that looks like a0 plus a1t, some polynomial p of t. T is the variable. So you can add polynomials. If you add two linear polynomials, you get a linear polynomial. This also includes the constants. This is all polynomials of degree of most 1, and you can multiply by a scalar. Or you can look at all polynomials, polynomials of any degree. The set of all polynomials is a vector space. In calculus, let's call, say, C01. This is the set of all continuous functions from the unit interval 0, 1 into the real, just what you studied in calculus. Because one of the theorems in calculus is that the sum of two continuous functions is continuous, and if you multiply a continuous function by another continuous, by a scalar, you get a continuous function. So, and in the universe, there are many, 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 many vector spaces. That's what we study in linear algebra. Linear algebra, in a certain sense, starts with linear equations, but then you move on to more general things. Now, suppose you have in a vector space V, that V1 up to Vk be vectors. This means these are elements in the vector space V. And let C1, C2 up to C sub k, that these be scalars in the field F, which is for us usually the real numbers. Then we define a linear combination of vectors. Multiply the vector V1 by the scalar C1. Multiply the vector V2 by the scalar C2, and so forth. Multiply the vector Vk by the scalar Ck, and add them all up. This is a linear combination of the vectors V1 up to Vk. And we say that the vectors V1 up to Vk are linearly dependent if there exist scalars C1 up to Ck, not all 0. Some can be 0, but not all 0, such that the linear combination C1 V1, C2 V2 up to Ck Vk is the 0 vector. And we say the vectors V1 up to Vk are linearly independent if they're not linearly dependent, which means that if C1 up to Ck are scalars, such that my linear combination is the 0 vector, then all of the scalars are 0. Every scalar is 0. And we've seen numerous examples of sets of vectors in R2 or R3, which were linearly dependent or linearly independent. Now, the first important theorem about linear dependence and independence says the following. Suppose we have a sequence of linearly independent vectors. Let x1 up to xk and y1 up to yk be scalars, numbers. Look at the linear combination x1 v1 up to xk vk. And look at the linear combination y1 v1 up to yk vk. If these are equal, then x1 equals y1, x2 equals y2, xk equals yk. That is, you have to have exactly the same numbers in the same positions on both sides of this equation. So what this important theorem says is, if you have linearly independent vectors, the representation of a vector as a linear combination of the vectors in your linearly independent set is unique. A given vector has at most one representation as a linear combination. And the proof is straightforward. If you have x1 v1 plus x2 v2 up to xk vk equal to y1 v1 plus y2 v2 up to yk vk, if two things are equal, then when you subtract them, you get 0. 0 is x1 v1 plus x2 v2 up to xk vk minus y1 v1 plus y2 v2 plus yk vk. Right? If these two things are equal, their difference is 0. But I can write this as a linear combination. This is just x1 minus y1 times v1. Right? Now here we have x1 v1, here y1 v1. When you subtract, that's x1 minus y1 times v1 plus x2 minus y2 v2 and so forth up to xk minus yk times vk. That's the 0 vector. But this is a linear combination of v1, v2 up to v sub k with these coefficients. So v1, v2 up to v sub k, linearly independent, means all of the coefficients have to be 0. x1 minus y1, x2 minus y2, and so forth. xk minus yk is 0, which means that they're all the same. xi equals yi for all I. And that's what we needed to prove. So, okay. We also have, just as we saw when we were studying linear equations, the general notion of a subspace. A subset W of a vector space V is a vector subspace if, first of all, the 0 vector is in W. Second, if W1 and W2 are two vectors in W, then the sum is in W. And if a vector W is in W and C is a scalar, then C times W is in W. So a subspace of a vector space is a subset that contains 0 and is closed under vector addition and scalar multiplication. So it's always interesting to know the subspaces of a vector space. And there's a way to build to get new subspaces out of old subspaces. So in general, for sets, and in particular for subspaces, so this is a little theorem also. Suppose W1, W2 up to WK are subspaces of a vector space V. Then if we take what is called the intersection, right, this symbol is called intersection. This means all vectors W and V such that W is in every single one of these sets. It's in W sub I for all I from 1 to K. So let's call this W. So W is the intersection of a finite number of subspaces. And the theorem says that this intersection is also a subspace. So the intersection of subspaces is a subspace. And how does the proof go? So for all I, Wi is a subspace. So 0 is in Wi for all I, which means 0 is in the intersection of all the Wi's, which is W. So this argument proves that W contains the 0 vector. Suppose W and W prime are two vectors in W. That means W is in W sub I, and W prime is also in W sub I for all I. But if these are both in Wi and Wi is a subspace, W plus W prime is in W sub I for all I, which means W plus W prime is in the intersection W. So this is a one-line, two-line proof that this intersection of subspaces is closed under vector addition. And similarly, let W be in W and let C be a scalar. So W is in W sub I for all I, and Wi as a subspace is closed under scalar multiplication. So CW is in W sub I for all I, which means CW is in the intersection, capital W. So I just proved that if you have subspaces, their intersection contains 0, closed under vector addition, closed under scalar multiplication. Therefore, it's a subspace. Any questions about any of this? So we're now starting really linear algebra, which is the study of vector spaces and certain functions between them. So there's a simple result that says the following. So we have V as a vector space, and let S be a non-empty subset of V. Let W be the set of all linear combinations of vectors in S, then W is a subspace. So, and the vocabulary we use here is that the set S generates the subspace W, or equivalently, the subspace W is generated by S, in the sense that every element of W is a linear combination of vectors in S. And the proof is as follows. First of all, S is not empty. So if you choose a vector S in S, 0 times S, which is the 0 vector, that's a linear combination of vectors in S. That's in W. So W contains 0. And if W is some linear combination of vectors S1 up to S sub k in S, then C times W for any scalar is C times this vector. But by distributivity, this is CC1 times S, and so forth up to CCK times S sub k. And this is another linear combination of vectors in S, so this is in W. And if W is this vector, and if we have, let's say, W prime, which is C1 prime, S1 prime, some other linear combination, W plus W prime, it's just this plus this. C1 S1 up to CK SK plus C1 prime S1 up to CK prime SK. This L. But it's some big linear combination of vectors in S. So this is also in W. So the set W also is closed under scalar multiplication and vector addition and contains 0. So that proves our theorem. Okay. So I've introduced two fundamental notions in linear algebra. So we have, notion 1 is linear independence of a set of vectors. And notion 2 is what it means for to say that a subspace W is generated by a set S. So to say that W is generated by S, or same thing, S generates W, this means that W contains every linear combination of vectors in S, and every linear combination of vectors in S is in W. Set of vectors is linearly independent if the only linear combination of the vectors that gives you the 0 vector is the trivial linear combination where every vector is multiplied by 0. So we have these two notions, and they go together to prove the following theorem, which turns out to be one of the fundamental theorems in linear algebra. And we prove it by using one of the fundamental theorems from chapter 1 about linear equations. So this theorem says the following. suppose that S is a set of m vectors, W1, W2 up to W sub m. That's a subset of V. And let W be the subspace of V generated by S. That means that every vector in W is a linear combination of vectors in S. So I have m vectors in my generating set. Suppose I take a set of V1 up to V sub n vectors in W. So the theorem says that if n is bigger than m, then the vectors V1 up to Vn are linearly dependent. So if I have m vectors that generate a subspace W and n vectors in W, if there are more vectors that I choose than vectors in the generating set, then these vectors have to be linearly dependent. And I want to do the proof carefully because this is really very, very, very important. So for each j from 1 up to n, the vector vj, this is a vector in W. And so v sub j is generated by the set S, which consists of these m vectors, W1 up to Wm. Therefore, Vj is a linear combination of these vectors. It's A1j W1 plus A2j W2 up to A sub mj Wj. Or in sigma notation, this is summation. I goes from 1 up to m, A sub ij, W sub j. Every vector in W is a linear combination of this set W1 up to, sorry, this should be going up to, mj, that's right. So each of these n vectors is a linear combination of the m vectors in the set S. So suppose that x1 up to xn be scalars such that this linear combination x1 v1 plus x2 v2 up to xn v sub n is the zero vector. I want to know if I can find scalars not all zero such that this linear combination of the v's is zero. But remember, each vj is some linear combination of the w's, because the w's are in the set S. So let me write this. I can write this. This is summation. J goes from 1 up to n, x sub j vj. But vj I can write like this. So this is summation. J goes from 1 up to n, x sub j, summation I goes from 1 up to m, aij wi. I can move this in there. This is summation j goes from 1 up to n, summation I goes from 1 up to m, a sub ij, x sub j, wi. And finite summations can be interchanged. This is summation I goes from 1 up to m, j goes from 1 up to n, aij, wj, sorry, aij x sub j, w sub I. I mean, this is a linear combination of the wi's, right? Each v1 up to vn is a linear combination of the wi's. If I take this linear combination, I get another linear combination. And I want to know whether this is the zero vector. Sorry, I want to know whether I can find x's such that this is the zero vector and the x's aren't all zero. So one way to get this to be the zero vector is if all these coefficients turns out to be zero. So suppose summation j goes from 1 up to n, aij xj equals 0 for all I from 1 up to m. Let me write this out. So when I is equal to 1, this is a linear equation that's homogeneous. A11 x1, A12 x2, up to A1n xn equals 0. For I equal 2, I have the equation A21 x1 plus A22 x2, up to A2n xn equals 0. And so on for I going from 1 up to m. When I get to the last equation, when I equals m, this is am1 x1 plus am2 x2 plus amn xn equals 0. So this is a system of how many equations? M, homogeneous, the right-hand sides are all 0, homogeneous equations in n variables. And the big theorem in chapter 1 said if you have m equations and n variables, if m is less than n, if there are more variables than equations, then there is a non-zero vector x1 up to xn that is a solution. So, but that's exactly our situation. What did our theorem start with? We have, back here. We have a set of m vectors in the set S. W is generated by this set of m vectors. In this subspace W, we choose n vectors. So each of these vectors is a linear combination of the W's. And we're choosing more vectors than there are vectors in the generating set. And I wanted to prove that the vectors v1 up to vn are linearly dependent. And that comes down to knowing whether this system of homogeneous equations has a non-zero solution. And it does, because there are more variables than equations. So we're done. You can find x's not all 0 that solve these equations, which means this linear combination of the vectors v1 up to vn is the 0 vector, and not every x is 0. So that is the proof of this theorem. I'm going to prove this several times in the semester just because it's so important. And you really have to learn and understand it. Now, in geometry, we have this rough notion of dimension. So you think of a line as being one-dimensional. And you think of a plane as being two-dimensional. And you think of, let's say, a cube, a solid cube, as being three-dimensional. And you would expect that there are spaces, objects in geometry that would naturally be four-dimensional or five-dimensional, and so on, any dimension, but we're only used to three-dimensional space, so humans cannot draw shapes of dimensions strictly bigger than 3, but that doesn't mean they don't exist. It just means we can't draw them. So that's the way it is. But we would like to assign, our goal is to assign a dimension to every vector space. Right? We'd like to somehow to define the dimension of a vector space, which generalizes what we grew up believing and knowing. And for that, we need to obtain or construct the idea of a basis of a vector space. So a basis of a vector space is going to be a set that generates the vector space and is linearly independent. So every vector has a unique representation as a linear combination of the vectors in the basis. And another fundamental theorem in linear algebra says if you have two bases for a vector space, the bases have exactly the same number of elements. And once you know they have the same number of elements, that's an integer you've assigned to the vector space, and that's what we call the dimension. So what we're going to do tomorrow, right? You will have taken the exam this afternoon, so your head is clear, is to begin to talk about bases and dimension for vector spaces, right? That's kind of our preview of coming attractions. So that, I think, is enough for today. And I will pause at this point.